Trent.
Yep, what's up?
Would you be able to look at something and heat transfer?
Sure.
We're trying to do our lab and everybody in my class is kind of lost
Hmm.
on the guide that you gave us. It's basically, he gave us all, like, we've all taken this for 476B.
Okay.
And he wants us to find the total heat transfer for the hot and cold part pipe. But I'm just confused on which equation I would use if it would be for. I would use this one, what's the LTP temperature on that, or if I would go through, because I'm confused on the difference between the theoretical and experimental. Is this going to be the theoretical that we?
Okay. So is this a heat exchanger?
Yeah, heat exchanger.
Oh, okay.
Pipe.
Yeah. So for heat exchangers, you have two pipes that are exchanging with each other, and for both pipes there's going to be a difference. They're going to start at a temperature and they're going to end at a temperature. And so usually for heat exchanger, I use the volume temperature difference.
Okay.
Because that accounts for the fact that both pipes are going to be changing temperatures. Right? Okay. And so the temperature difference between them is going to vary, down the line.
Okay. Would I put in, like, say I find effectiveness?
Yeah.
Could I then just put it and manipulate this into Q equals effectiveness times Q max?
Yeah.
And that's what my experimental Q or the heat transfer theoretically should be?
Right. So the effectiveness is so Q max is like the theoretical absolute maximum temperature. You're never going to reach that because of thermodynamics. And so if you know the effectiveness, then the effectiveness is just like a percentage of what Q max is. And so you take your Q max, you multiply by the effectiveness, which is some number between 0 and 1, and that's how you get how much Q you should have gotten, how much heat transfer you should get.
So it's like that's your theoretical taking into account resistance.
Exactly. Yeah.
Okay. Cool. Thank you.
Yeah.
I think we just get theoretical values for this lab. I thought we were just calculating experimental values and comparing.
That's what
the shade.
I guess because when I asked in class, it said that this was a theoretical that we had. Like,
Yeah.
So I think we compare that to manipulate this, right?
Yeah.
Find effectiveness.
The effectiveness.
And Q, and then you compare that to
The Q we get from
which is
UA
this.
delta Q. Oh, that one, yeah.
or you can do that one. Yeah.
Either way, it's a Q. Yeah.
So I think
What was your name on this? He was
A
A is the surface area. Delta TF is Q was. It tells you at the top. I can't remember what it was.
use like your resistance. It's like
Yeah, it's a total
reduction.
reduction. Yeah.
Convention.
Which I don't know why they use for that. So I was confused. So it's a bunch of people who just like what? We're using you. The variables same across class, please. Oh yeah, I was cranking out of that. How long are you here? I don't know. I fell asleep, woke up. I'm like, oh, it's almost 3. And I was probably out there for like 30 or so minutes.
Four years I've been there. Even like so, you know, there's like hemp products, you know, whatever, all that stuff. People have taken that and it's shown up on tests. And it's really honest. You know, there's like hemp canola, hemp, like all this stuff. You can't take that. That's fine. Within reason. Can't. Injection is one of the biggest issues. Can't go, you can't be seen at the bar, especially. You can't. I mean, to a degree, but the opposite is the opposite. You gotta know your crowd, you gotta see your environment. Oh,
I have kind of an interesting question. I always think about this. So so say you have a window, right?
Yep.
And outside, we'll say it's like a cooler temperature of like 60 degrees. Inside, it's like a hot temperature of 75 degrees.
Okay.
Now, you know how like with windows, it kind of has like the blinds are angled like this.
Yep.
So I always make sure I turn it so that the cold side is out here and the hot side is out here. I fight with him all the time on this. So the reason I turn this is because my thought process is cold air tends to go down while hot air tends to go up.
Okay.
So I thought that turning this way would make the heat transfer more effective to bring the cold air in and let the hot air escape.
I see.
Does that really make a difference, or am I just overthinking it and it's not really going to do anything?
With the sunlight blast my eyes at 7
Just
o'clock.
change the angle of it. Because he sleeps next to the window and the light's able to come in.
I see. I see.
Well, I'd rather sleep cold and then turn it later.
I mean, I think your logic is sound. I think it would make a difference. I don't know if it would make like a huge difference, in the actual temperature of the room.
Okay.
Although I mean that's just my own impression though. But I know that when I was in grad school, there was a huge study of studying one of the big buildings on campus where they wanted to cool it without actually using air conditioning. And part of their scheme was to do, kind of release the shutters or like turn them a certain way at night, such that it kind of improves the airflow. I don't know if they did this, and for that one, like the building is a lot, the shutters are a lot bigger for that one too. So
These are also like basic plastics, so obviously, the heat transfer between these materials is probably not that substantial. So even if they were closed, the heat would probably still go through pretty easily.
I mean, the only way to find out is to put thermometers in your room and then test
I guess,
it, right?
it
One
was
way
to test it. But that's a little hard, a little too many uncontrolled things. But, yeah, it was just something I was curious about because I want to get him to turn them that way.
I see.
I don't know. In my mind, I'm
Absolutely
like, it's
not.
better if I do this. But yeah, that was just like some little thing I was curious about.
I see.
Thanks.
Yeah.
My eyes, dude. Wake up at 7 o'clock.
Get up at 7 o'clock anyway.
Sit next to you. Oh, still Bailey. I like Bailey. Gets in here.
Dude, there's so many little things in the house that I always do that to like make sure everything's gonna fit. Like I place my fan in a certain part of the room, open up certain windows, and like this is the maximum airflow to the house. And I might be right, or I might just be have a say. Who knows? What if your engineers are all like that? How many times we argue about like little stupid stuff like that where we just start actually bringing in and shit about every single wait a minute. Take the structural down. You ever think about oh, those are mine. I do. Oh, yeah. Have you ever seen the problem where you have a pot, yeah, right? It's full of boiling water, and you have a bucket here that also has water inside of it. This water is boiling, it is boiling the exact same. Okay, you guys have weird things you probably
I'll get all of these. Yeah, I know. What color? Look over here.
All right, it's 4 o'clock, so let's go and get started. Good afternoon, everyone. How's everyone doing today? Doing good, doing good. All right, and so Tuesday was our first time with the software, and so I just realized, I think Tuesday night, that the announcement I wrote last Friday didn't properly send, maybe because I got that announcement in my email like literally after the workshop. I was like, oh, well, and this is why probably a lot of people didn't have it installed, and so I apologize for that. I wrote that announcement last Friday, but I guess there was some issue on Canvas and it didn't send. And so, you know, if you haven't had a chance to download the software, you know, please do and get started on that tutorial. Okay. And if you run into any issues with anything, just let me know. And don't feel like it's a bother. Literally, you know, it's a research software. If there weren't issues with research software, then, you know, we should sell it. And so the reason we don't sell it is because there's probably still some issues with it. So and so don't feel bad if you have issues. Just let me know, and I'll do my best to help out. Yeah.
One thing too is they actually just updated for a Windows version.
I saw that.
January
Yes.
15th,
Yeah.
so I don't know if anyone knew that yet.
Yeah. So if you have Windows, they did release a newer version for February 15th. It shouldn't have. I mean, we're mostly just using the core functionality. Usually when they have updates, they add some auxiliary features, and so it shouldn't affect what we do too much in the class.
Okay.
But it's always good to have the latest version.
Cool.
If anything, just for bug testing purposes too, for them. Yeah, what I do every time I teach, well, I mean, last year when I taught this class, I had a litany of bugs that everyone ran into in the class. I sent them to the developers. They took a week to get back to me because they're upset with me, and then they're like, okay, we'll fix these issues. So, and so I anticipate something like that's going to happen this semester as well. Okay.
What's your role again at that company?
So I used to be a developer, and so this was back when I was in grad school, and so this software was basically a product. We call it a product, but we don't sell it. That we worked on as a lab to kind of put out there as open source. Yeah. So I'm a former developer. Now I'm in my next life as an instructor, and so it's on to the next batch of developers at the lab. Yeah. Okay, and so the plan for today is we're going to continue on with the lecture notes we started last Thursday. Okay, and so those lecture notes were titled Arterial Biomechanics. And so we're going to continue on with that. I think we'll reach maybe about a little bit over halfway today, or at least that's my goal. And then we'll continue on next week. Okay. Another announcement. Next Thursday, I plan to have a guest speaker come in. Okay, so next Thursday we're going to have a guest speaker. I think her name is Cecilia. And so this is all part of the Professor for a Day program that you may or may not be aware of. Where next week is ECS week, and so a lot of your classes next week will probably start bringing in guest professors to give a lecture. And so I've only exchanged one email with our guest speaker, but my impression is that she's an alumni of Cal State Fullerton. And so she's going to give a talk on kind of the work that she does, which is involved with helping students kind of make that jump from from classroom to real life jobs. And so what I asked her was to give like a workshop on what she thought was some of the more soft skills that aren't normally taught in the classroom that would be most helpful for you guys to get a job. Because I know a lot of you guys are seniors, or you guys are grad students, or are going to be looking on the job market soon. And so, I thought it would be something that would be, good for this audience. Okay, and so that's all my announcements. And so, are there any questions I can answer before we get started? Okay. All right, so let's go ahead and let's get rolling. Okay, and so we left off on our topic of arterial biomechanics. And this whole unit, or this whole set of notes here, will be on describing the biomechanics, or in other words, the physics of the blood flow in our arteries. Okay. And if you remember from our discussion of our anatomy and physiology, arteries are blood vessels that take blood away from the heart. Okay. Right. And so if you compare the fluid mechanics of your blood flow in your arteries versus your veins, your arteries tend to have much higher pressures and much higher flows, okay? Flow rates. Remember, your veins are the blood vessels that bring the blood back to your heart, okay? Another important characteristic of arterial blood flow is that they're much more pulsatile, okay? Okay. And remember question.
Is the increased pressure and flow rate due to the fact that there's oxygen in the system at that point? Or-
No, it's more due to their proximity to the heart. And so the heart is the main pump. And so basically right after the heart pumps, then it goes into the arteries. Yeah. Mm-hmm. Yeah, by the time we'll talk about veins, kind of much later in the class, but once the blood reaches the veins, they've kind of lost a lot of their energy. And so, just by conservation of mass, the blood has to make its way back to the heart. But veins tend to be kind of bigger, and so they have lower pressure and lower flow rates than arteries.
So which one would you tend to see more disturbances in, the arteries or the veins?
Definitely the arteries. Yeah.
Because of the higher pressure?
Yeah. Yeah. I mean, veins have their issues too. So I mean, there's conditions out there. You've probably heard of like varicose veins. But if you compare the amount of like issues that can pop up in the arterial system versus veins, there's way more issues with the arterial system than with veins. Yeah. Right. So remember, the pulsatility arises from the fact that arteries are they're most connected to the heart, and every time the heart beats, that's going to cause a spike in like pressures and flow rates in the arterial system. if you compare that to the flow in the veins and even in the capillaries, the flow in the capillaries and the veins tend to be a lot more constant. And so it's almost constant flow in your capillaries and the veins compared to the arteries. Okay? And so, for that reason, we spend, the majority of this class and for your final projects too, focusing on arterial flow, because that's kind of where most of the medical interest is. Okay, and so to that end, we started talking about the waveforms that you can have. Right. And so on the one hand, we have the pressure waveforms and the flow. All right, so the pressure waveforms look something like this. Right, and the flow waveforms, at least one example of the flow waveforms, if you measured it right next to the heart, would look something like that. Okay. And so on the x-axis here, this is time. And so these are basically measured as a function of time. And on the y-axis here, we have pressure. And here we have flow. Okay. Right. And so this is what I mean by pulsatility. And so you have periods of where the pressures and the flows are spiking upwards, and then you have a period of relaxation when the curves come down. Okay. And remember, we distinguish between the two phases of the waveform based on what the heart is doing. Right. And so on the one hand here we have systole. Okay. And so when pressures and flows are rising up, actually, I think this one. Okay. And so when the pressures and flows are rising up, that's when the heart is contracting, right? So remember, systole means heart contraction. Okay. And when the heart is relaxing, we call that phase diastole. And remember, the typical heartbeat for a person, well, I mean, everyone's really different, and it depends on how healthy you are. But a good average, heartbeat would be about 1 second. So all this happens really quickly. And so, you see your blood pressure rise and fall, within the course of a second. So it's not like a slow increase or decrease, which might, just kind of, we'll be focusing so much on this, it might seem like it slowly goes up and down. But all this happens every single second. So your blood pressure is going up and down, really, really quickly in your system. Okay. All right. And so, last time we talked just kind of some general characteristics of these, but today I want to focus a lot more on the pressure waveform. Okay. Basically, what kinds of properties in the cardiovascular system affect the pressure waveform, and how we can actually model it. And so, how can we actually, build maybe an experimental rig to model this pressure waveform? All right, any questions on this? Okay. All right, and so to that end, I want to discuss one of the first attempts to model the pressure waveform, or to basically recreate it in a lab, called the Windkessel model. So Windkessel, if you're not aware of the origins of that word, Windkessel, I believe, is a German word. Yeah. And what it stands for is air chamber. And so since it's German, I'm probably butchering the pronunciation, but that's okay. Literally everyone calls it Windkessel. Okay. And so, Windkessels are a very old concept. And so people, for a long time, people have always been fascinated by, just learning more about the cardiovascular system, how we can recreate it, how can we study it, so that we can come up with improved studies. And so, the Windkessel was one of the very first kind of early attempts, I would say one of the early successful attempts to recreate the pressure waveform. And through its development, we actually learned a lot about how the cardiovascular system works in terms of, what are some of the key kind of physical features of the cardiovascular system that contribute to the waveform. Okay. And so when these scientists set out to develop the Windkessel model, they had a few goals. Okay. In other words, they observed certain features of the pressure waveform inside humans that they wanted to replicate in the lab. Okay. One key feature that they wanted to replicate for sure is the fact that the pressure waveform never goes down to zero. Okay. Okay. Right. So even though it's true that your heart isn't contracting all the time, right, and so it has to relax every now and then, but even when the heart relaxes, we don't have the pressure just suddenly drop down to zero, right? And you can see that if you go to like CVS and measure your blood pressure as well, right? And so if you go to CVS, they give you two, right? They give you like two numbers, where the first number is the maximum or the peak blood pressure that's achieved in your system, and the second number is the minimum. Right? So the fact that the minimum here is not zero is very interesting. Okay, and that's something that they wanted to account for in their model. Okay. All right, and so the big reason, and I might have mentioned this last time too, the big reason why the pressure never goes down to zero is the fact that your larger arteries are compliant. Okay. Okay. Compliant is another word to say that they're flexible, right? And so they're not rigid tubes. They actually have some give in their wall, so they can expand. And by virtue of that, the fact that they can expand, that means they can temporarily store blood. Okay. And so this stored blood eventually gets ejected, and so it doesn't stay in the large vessels forever. And so when the heart is relaxing, then this stored blood kind of gets slowly ejected through the rest of your system. Okay. Okay. All right. And so this is one unique factor, right? And so the fact that your large vessels are compliant and they can store flow is the reason why your pressure never goes down to zero. And so that was a big piece of behavior that the scientists wanted to replicate. Okay. Another consequence of this is that because your pressure never goes down to zero, that means there's always a mean pressure. There's always an average pressure inside your system. Okay, so in other words, you can say that your blood flow is always pressurized. Okay. And so even though there's some pulsatility, so even though the blood waveform or the blood pressure waveform goes up and down, there's always a mean pressure. There's always an average pressure that it oscillates around. Okay. And this plays another important role as well, right? And so the purpose of the mean pressure is to drive the flow through the capillaries. Okay? Okay. Right. Because remember we talked about last time that the oxygen needs and the nutrient needs of like your muscles and your nerves and all the organs in your body, a lot of times they can't wait for the blood to to pulse up. And so in order to ensure that there's a constant feed of like oxygen and nutrients in your muscles, there needs to be a mean pressure there to drive a constant amount of blood. Okay? And so even though you see the blood flow in your arteries go up and down, if you measure the blood flow in your capillaries, they're actually close to constant, and that's essentially just to make sure that your capillaries get a constant feed. Okay? And so another consequence of having this mean pressure is to essentially always make sure that we have that constant flow through the capillaries. Okay. And so the model that the scientists wanted to, or the Windkessel model that they were developing, wanted to make sure that these properties were captured. All right. Any questions on this? Yeah.
I think it's a little off topic, and I may be totally off, but I think with the aneurysms, that's is that like the whole one, right?
Yeah. So aneurysms are when you have kind of an expansion of your blood vessel, and so normally your blood vessels are nice tubes. An aneurysm is when it either flares up and becomes like a balloon, or I think the one you're thinking of is when there's kind of like a sac of blood that forms off to the side. So yeah, aneurysms are really fascinating, and I don't think I have any data sets for aneurysms for your final project, but I've worked with them before. I've done some simulations of them before, and the physics inside them is really interesting. And it's getting a little bit off topic, but the fascinating thing is that the scientists can't agree on what causes aneurysms and what causes them to burst. And so part of the reason there hasn't really been any advancement is that there's kind of two camps. And so it's funny because like you go to a meeting with these aneurysm people, and it's like almost like going to a Twilight convention. So you have like, I won't get into the details, but there's basically like a team Jacob and a team, I forgot the other guy. And then they go at each other like they're all a bunch of fangirls. And so because they can't agree, then the field hasn't been able to advance. And so yeah, it's kind of a funny thing, but yeah.
So it's not because vessels not the
It's that's part of the debate. It's what factors of the blood vessel actually do that. But I think we'll get into aneurysms later, because I think I have a unit in this class about cardiovascular diseases. I'm not sure when that is. I think in a few weeks, and so we'll talk a lot more about aneurysms. Any other questions on this? Okay. All right, and so to kind of summarize this stuff, there's kind of two, I like to call two core behaviors of arterial blood flow, and they're kind of based off these two points here. All right, so the first core behavior is regarding the large arteries. Okay. Okay. right? And so that's one of the core behaviors of the cardiovascular system. And the effect that this ultimately has on the pressure waveform is that it determines the peak-to-peak amplitude, okay? Okay. And so if you have more compliance or less compliance, that's going to determine, how far apart your maximum and minimum pressure is. Okay. Okay. And so the other core behavior of arterial blood flow is with regards to the capillaries or the tiny vessels. Okay. And the main fluid mechanical factor of these small vessels is their viscous resistance. Okay. And so because the capillaries are so small, right, the amount of viscous friction inside them is tremendous compared to the larger arteries. Okay. And so the viscous resistance of these smaller vessels requires a large mean pressure to squeeze blood flow through them at a constant rate. Okay. So those are the two core behaviors. And so these are the main behaviors that the Windkessel model has to accomplish. Okay. Okay, and so to that end, the classical Windkessel model has three components. Okay. Oh, and there's the third one, I guess, as well, is the heart. The heart is the pump. Okay. We can't forget about that. But we focus mostly on the blood vessels because that's what we're focusing in this class. Okay. And so the three components of the Windkessel model are, one is the pump. Okay. Okay. And so in this case, it's just a mechanical pump. Okay. But it's meant to represent the heart. Okay. Two is an elastic chamber. Basically, it's basically just like a big water balloon. You can think of it like that. Okay. And three is a bunch of small, tiny microchannels. Okay. And these represent the three core behaviors that I've listed above. Okay. So visually, it looks something like this. And so we have a pump. Right. And so this is where the blood is going to come through. Okay. Then it feeds directly into an elastic chamber. Okay. Okay. Then the fluid is going to feed into all these tiny microchannels. Okay. Okay. Right, and so that's it. And so we have these three components that are connected together. And of course, there has to be a feed here, and so there has to be fluid that comes in. Okay. And so the way that they worked this was that when the pump here was basically like another chamber that you can kind of squeeze. Okay. And so when the pump squeezed, okay. And so when the pump squeezes together, then the pump itself gets smaller. Okay. Right. And so that's the model, the same thing as when your heart contracts, right? And so when your heart contracts, it basically squeezes the blood out. Okay. And so the first thing that the blood does when it comes out is that it of course is going to fill the elastic chamber. And so the elastic chamber is going to get bigger. Okay. Right, so some of that flow is going to fill the elastic chamber, but some of it's going to go through, right? And so because there's no valve on the elastic chamber, some of the flow is going to fill the chamber, but some of it's going to go through, right? And so this first phase where the elastic chamber fills, this is systole, right? And so this is when the heart is contracting. And then the next phase, when the pump has to expand again, or when the pump has to relax, we have a valve here that kind of shuts it off, right? And so when the valve or when the pump is relaxing, then the elastic chamber is naturally going to start deflating. Okay? Right, and so the pump is going to return to kind of its original size. Okay. The elastic chamber is going to start to return to its original size. Okay. And then as it deflates, it's going to push blood through the microchannels. Okay. And so this here would be diastole. Okay. And so as elastic chamber deflates, okay, blood will be pushed through the microchambers. Okay. And so let me kind of show both of these at the same time. Right? And so this was kind of one of the first models that attempted to replicate the flow and pressure waveforms inside a person's body. Okay. And so when the heart is pumping, or when the pump pumps, right, then the elastic chamber is going to fill, and as the chamber fills, the pressure is going to go up just because there's more fluid in there, right? And then when the pump relaxes, that elastic chamber is going to kind of passively kind of deflate, right? And so the rate at which the chamber deflates, is a lot slower than when the pump is actually pumping. And so what you get is kind of a sharp increase in pressure when the pump pumps, and then there's a slow decrease in pressure as the elastic chamber deflates. Okay, and then that process just repeats all over again. So fast upturn and then slow decrease.
Yeah. So is there like a valve controlling so that the elastic chamber doesn't actually pump back into the pump?
It is. Yeah.
Oh, okay.
Yeah. So when the pump is kind of relaxing, then there's a valve that shuts off here.
Oh, yeah, yeah. Sorry.
And so when the chamber is relaxing, then the flow only goes one way. Okay. Right. And another feature of the Windkessel that works out really well is that you can see in both phases here, we have flow that's going through the microchannels, right? And so during during systole, when the heart is pumping, right, there's flow that goes through the microchannels because the elastic chamber can't hold all of it, right? So you have a huge influx of blood that comes in, and even though some of it fills the chamber, some of it does go through the exit. So some of it does flow through the microchannels. And during diastole, when the elastic chamber is deflating, right, because there's a valve here that's making sure that the blood can't come back to the heart, all that deflated blood is going to go through the microchannels. And so in both phases, you get kind of a constant feed of blood through your capillaries to feed your muscles and your organs. Yeah.
Question based off of what I'm saying with the valve.
Mhm.
So if there's a valve that shuts there, when the pump contracts, gets super small and the valve shut, wouldn't that be like a vacuum system that would prevent it from going back to normal size?
Yes, and so that's the purpose of the atria in your heart. And so the atria, remember, those are the chambers that that kind of catch the blood when they come back. And so there's one crucial part of your cardiovascular system that doesn't have the valve, and that's blood that's coming right back into the heart. And so that system is not valved. And so because of that, when the heart is relaxing, it basically vacuums up blood from the atria that kind of fills in at a constant rate when the other stuff is going. Yeah, good question. And that's kind of the purpose of having kind of dual chambers, is that that vacuum effect doesn't negatively affect anything else. Yeah. Right. So this is one of the first systems, and I believe it was actually developed in the late 1800s actually. So very, very early, but it was really successful in capturing a lot of these properties. And so what they did was that they basically once they constructed their machine, they were able to measure the pressure here. So this might have been during the time of like manometers. And so they actually had fluid filled columns that kind of go up and down, and they were able to observe in those columns the exact pressure waveforms that they were looking for. And of course they can measure the flow that's coming out the microchannels, right? And the flow that they observed was exactly what they envisioned too. So this was kind of one of the early models of blood flow, right? And this behavior here that I described before, this was kind of discovered as a result of studying this Windkessel model, right? And so the scientists developed these Windkessel models, and they were able to kind of determine what these properties are based on that. And so even to this day, this Windkessel model is still kind of a very influential breakthrough in the field that helped us understand a lot of the biomechanics inside our bodies. Okay. All right. Any questions on this? And in the community of cardiovascular biomechanics, we still kind of pay homage to the Windkessel model and a lot of the other stuff that we do. And so next week we're going to go over something called lump parameter models. Or actually, no, maybe not next week because you have the guest speaker, but the week after that, we'll go over lump parameter models, which are basically circuit representations of your blood flow. And so if you thought circuits would die with the circuits class, I have a surprise for you. So we use circuits in this class. Circuits are really helpful, and so you can use them in heat transfer, you can use them in fluid mechanics, and so they have a lot of really great applications. And there's a certain arrangement of a certain circuit that's basically meant to model this Windkessel, and we actually call it like a Windkessel circuit, Windkessel circuit, model, and that's the kind of the pay homage to this model. Okay, and so that's the Windkessel model, and so very very nice, relatively simple model, but I think it captures a lot of the biomechanics inside the arterial system. And so the next thing I want to talk about is wave propagation. A lot of my heat transfer students, 407 students that I'm teaching this semester, are kind of dying right now because they some of them have never seen circuits before, and I thought circuits was something you take before heat transfer, but a lot of them have never seen a circuit before in their life, and so they're kind of dying right now. And so I'm trying to teach them circuits, for the first time ever. Okay, all right, and so let's talk about wave propagation. So the Windkessel model that we just talked about, does a really good job of emulating the pressure and flow waveforms kind of on a global scale. But it does miss one very important aspect of the cardiovascular system that a Windkessel model is kind of, it can't actually replicate, which is this propagation known as wave propagation. Okay, and so to kind of start with, I'm gonna draw an analogy here, right? And so let's think of a string. Okay. And so let's say that this string is attached to a wall. Okay. And so one example that you can think of for this is like a guitar string, right? And so guitar string is essentially, a string that's, that's made of certain material. It's fixed at one point, and the other side is pulled with some tension, such that the string is taut. Okay. And so, let's assume that this string is being pulled with some tension T. Okay. So it's being tightly pulled. So there's no slack in the string at all. Okay. And so if you play guitar before, I'm saying that like I've played guitar. I don't play guitar, but I've watched people play guitar. What you'll know is that if you strum the string, right? Okay. Or if you pluck the string, or if you do something to it, right? What you'll see is that the string here is going to start to vibrate, right? And of course, that vibration produces a sound, and that's what makes guitars, such beautiful instruments. Okay. But if you slow down, and so if you took a very high-speed camera and you slowed down the exact point when you pluck the string, what you'll see is something like this. Okay. And so right after you pluck the string, you'll have a point where there's going to be a pulse that gets generated. Okay. Okay. Right, and so that's essentially the disturbance in the string that gets created when you pluck it, right? And because of the tension in the string, because you're pulling it, then that pulse is going to travel. Okay. And so if you kind of took the next frame of the high-speed video that you're recording, it might look something like this. Right? And so this pulse here is the exact same one as above. It's just kind of traveled down the string a little bit. Okay. And so this is after some time has passed. Okay. And of course, this pulse here is still traveling. Okay. All right, so what do we know about this pulse? And so we know that this pulse, it's traveling at a certain speed, and that speed is finite, right? And so that's something that we can actually measure. Okay. And what I mean by finite is that it exists, and so it's not infinity, and we can measure it and observe it. Okay. Okay. All right, so there are some factors that affect the speed at which that pulse travels. And so some of it has to do with the material properties of the string, right? And so if you use different string materials, it's going to cause the pulse to either travel faster or slower. Okay. But another factor that causes that changes the speed or affects the speed is the tension in the string, right? Okay. And so generally speaking, if you use a string of a stiffer material, or if you increase the amount of tension, then it'll, cause the pulse to move faster or slower. Okay. All right. And so the next thing I want to talk about is when the pulse reaches the wall. Okay. And so when you have a pulse that reaches the wall, what it does is it basically bounces off the wall and comes back. Okay. In other words, what we say is that the pulse is going to reflect off the wall. Strat. Spelling is hard. Okay. And so the pulse is literally going to hit the wall and it's going to start coming back. Okay. Okay. And for now, let's assume that after it reflects, it stays the same direction. Question.
But also the wall absorbs the pulse, right?
Sometimes. So if the wall is relatively compliant, then it's going to absorb that string, that pulse. But if it's perfectly rigid, then it's just going to keep bouncing back and forth. And throughout all this, we're assuming that there's no dissipation, because in reality, if you do pluck a string, there's like some friction and some stuff that causes the pulse to kind of get slower with time or smaller with time. But for now, we're assuming that none of that is there, and the pulse is just going to stay the same size, going to reflect off the wall and then come back. Yeah, good observation though.
Inside your body, what would be considered a wall?
Yeah, so inside your body, what we're leading up, what I'm kind of leading up to this is that, pressure pulses are going to travel across your blood vessels, but they're elastic. And so the wall that it hits is the capillary bed. And so the capillary bed are these really tiny, you can assume they're microchannels basically. And so because they're so small and they're a lot stiffer than your bigger blood vessels, then that's kind of the same thing as a pressure pulse hitting the wall and coming back. Yeah. Okay. And so, knowing that our pulses are going to reflect, let's talk about what happens when we send another pulse down. Okay. Okay. And so when we send another pulse, the new pulse and the old pulse, they're going to eventually meet. Okay. And they're going to have, nice pulse babies. No, just kidding. And so they're going to interact with each other, right? Okay. Right. And so let's say that we have a pulse here, another pulse. Right. So we have one pulse going this way, another pulse going that way. Okay. And eventually they're going to collide. And so if both pulses are the same sign, and so they're kind of facing the same direction, then they're going to add to each other. Okay. And so when they overlapping, you kind of have just one bigger pulse here. Okay. But what can also happen is if you have a pulse that's interacting with a pulse that's kind of in the opposite direction, okay? And so when this happens, then they subtract from each other. Okay, so you might see a little bit of a blip or something, but in other words, they kind of destruct each other, okay? Okay. And so this same phenomenon, even though we've kind of been talking about guitars this whole time, this concept happens in the cardiovascular system as well. Okay. And so in the cardiovascular system, the string will be like your blood vessel walls. Okay. Okay. the pulses that get generated, those are generated from the heart. And so when the heart contracts, that creates a pressure pulse or a pressure wave. Okay. And the wall, just like we talked about just now, is the capillary bed. Okay, and so these pressure pulses are going to reflect off the capillary bed. Okay. Okay. Okay, and so this wave propagation or this pressure wave, propagation is, a very important characteristic of arterial blood flow. Okay, and so there's kind of two things that are going on. And so if I draw kind of a typical blood vessel, okay, right, and so we're seeing a cross-sectional view of a blood vessel. Of course, when the heart pumps, when the heart contracts, it's going to push fluid down the interior of the blood vessel. Okay, so let me use red. Okay. Okay. And so this red here represents, blood flow or blood fluid flowing in the interior of the blood vessel. Okay. At the same time, right alongside the fluid, we have pulses that travel along the vessel wall. Okay. Typically speaking, the propagation speed is a lot faster than the blood fluid velocity. Okay, and so it varies depending on what part of the cardiovascular system that you're in, but it's generally about 5 times to 10 times faster than the blood fluid velocity. Okay. Okay. Right, and so these pressure pulses are traveling way faster than the blood can keep up. Okay, but there's two things, and so and this is a direct consequence of the fact that our blood vessels are these flexible structures, and they're not rigid. Okay. Okay. Any questions on this so far? Yeah.
So for it to pulse along the blood vessels, that means your blood vessels must be under tension.
Yes, they are.
And so if they're under tension and it's moving quite fast, what would happen if the tension is reduced on that?
Yeah. So then the propagation speed would drop then because the tension is being reduced.
And what would that lead to?
It's a good question, actually. It's I know that there's everyone has a certain degree of, they call it pre-stress inside your vessel wall. So that's kind of another way to say that there's tension. And that if you do like excise out some blood vessels from a person's body, it tends to kind of shrink up. And so the interesting thing about that is that it's been really hard to kind of measure the material properties of blood vessels because as soon as you take it out of someone to measure it, then it kind of automatically shrinks up. But I know that there's factors that for some people have more pre-stress than others. But I'm not sure what effect that has on their health. I'll have to look that up and come back to you. But yeah, it's it's an interesting phenomenon. Yeah.
I didn't imagine that like using a water hose. So probably just wiggles in a way.
Yeah. No, a water hose is a great example for that. So when you first turn on the water hose, there's a pressure pulse that travels down kind of when you first release the valve, and there's that kind of first wiggle that kind of goes down the water hose. That's exactly the same thing. Yeah, it goes really fast on a water hose. The water hose is usually pretty stiff compared to your blood vessels, but it's the same idea. Yeah.
Question.
Yeah.
So I know that the blood flow speed has been different.
Yeah. Mhm.
But on average, what is the typical blood flow speed?
So the typical blood flow velocity. Usually the order of magnitude that's usually used is usually centimeters per second. And so it's going to be on the order of like anywhere from like 5 to, I would say, 50 centimeters per second, depending on the blood vessel.
Just to follow, so the pressure wave speed, is that ever going to be like at the speed of sound?
No, it doesn't get that fast. Yeah, so it's definitely a lot faster than your blood flow speed, but yeah, it doesn't get up to the speed of sound. Yeah.
How would things like heat and cold, like if you applied heat or cold to your body, it constricts or expands the blood vessels? How does that affect the pressure wave?
Oh yeah, no, it has an effect because generally as you heat stuff up, things tend to get a little bit looser, and so the pre-stress tends to get lower when you heat stuff up, and so less tension means it's going to move slower. But if you're cold, things will tense up, and then it'll travel faster in those sense.
Okay.
Yeah. Yeah.
Does chemicals like play in that too? Like
Yep.
adrenaline?
Oh yeah. And so so there's a lot of chemical controls in your body as well. And so if you it's like adrenaline or something, and so part of the reason that there's pre-stress is that there's muscle inside your blood vessels. So they're called smooth muscles. And so those so you can send chemical signals, nerve signals as well, to tell the smooth muscle to either like contract or to kind of relax as well. And that has another effect on the wave propagation speed. Yeah. Yeah, good questions, guys. Any other questions on this? Okay. All right. And so the speed at which these pressure waves travel, we call these the wave propagation speed. And of course, it's affected by a lot of different factors. Okay, and so the next thing I want to discuss is what does this wave propagation actually do to the biomechanics? And so the fact that the wave propagation exists is of course it's really cool, but we want to talk about what kind of tangible effects it has on a person's health. Okay, and so I want to talk about two kind of big effects. And in particular, I want to talk about their effects on the pressure waveform that you observe. Okay. And so number one, as you get further away from the heart, the peak systolic pressure tends to increase. And so if you compare the blood flow waveform, right next to your heart versus, maybe in your arm or something, then the blood pressure in your arm, the peak pressure is actually going to be higher. And the main reason for this is because of the additive pulse reflections. And so when the pressure waves reflect off the capillaries, they're going to interact additively with the incoming waves. And so that leads to a higher pressure. Okay. You don't see this effect, in theory, like we were talking about before, in theory, if you don't have any dissipation, then the waves will just kind of keep reflecting back and forth. And so there should be, no difference in effect at the end of the tree versus at the beginning. But there is some dissipation. And so there is some friction in the pressure waves where, eventually over time, if the waves travel along the wall enough, it will kind of dissipate down to zero. And so that's why you don't see as much of these wave propagation effects closer to the heart, because by that time, after the wave reflects off the capillaries and comes all the way back, then it's probably dissipated a lot of its energy. But if you're closer to the capillary waves, then you kind of have you basically have almost two waves that are kind of interacting together at once. And so that's what leads to this higher pressure. Okay. And number two, the other effect that you have is that as you get further away from the heart, the peak systolic pressure tends to be delayed, compared to places earlier in the heart. Okay. Right, and of course that's also due to some wave reflections, but that's also due to the fact that pressure takes time to travel down the tree, so it's not an instantaneous thing. And so when the heart pumps, the blood vessels in your arm don't feel it right away, because it takes time for that pressure pulse to travel from your heart to your arm, and so that delay is kind of reflected in their waveforms. Okay. Right. Okay. So any questions on this before I draw these out? Okay. All right. So what do these look like in practice? And so if I kind of draw two waveforms here, so actually let me draw one. Okay, so here we have time. On the y-axis we have pressure. Okay. First, let me draw a waveform near the heart. And so in black right here, this is a pressure waveform near the heart. And if you compare that to a waveform, further away from the heart, it would look something like this. Okay. And so you can see here that the pink curve obviously reaches a higher maximum, right? But it's also delayed. And so if you look at where the peak pressure here is on the near heart waveform, and you compare that to where the peak is on the far from heart waveform, there's a little bit of a delay. And so that delay is due to the fact that, pressure waves propagate at a fixed finite speed. Okay. Okay. And so that's the illustration. And so, the next question I think that's fair to ask is, how do we compute the wave propagation speed? Okay. And so, unfortunately, there is no great formula for this yet. Partially, and so, another big factor that affects the propagation speed is all the bifurcations in your body. And so, because there's, the bifurcation pattern is really complex, and even to this day, we still don't have a good mapping of that yet. It's hard to get one good hard formula that encapsulates all of that. But we can come up with a very simple one for a simplified model. Okay. And so this is, you know, if you use this formula, it's not going to get you exactly the right speed for any given person, but it gets you in the right ballpark, and it has a lot of the right properties in its formula that, you know, that we like to see. And so one formula that we can have is we can have pulse PWV, which is a pulse wave velocity, is equal to square root of E times H divided by D times rho. Or I can define these variables here. So let's say that E here is a Young's modulus. H here is the thickness of the vessel wall. Okay. D here is the vessel diameter. And rho here is the blood density. Okay. And so I think this formula was developed analytically from a simple flexible tube. Okay. And so this would work if your blood vessel, if your cardiovascular system was just a single tube, but because we have all this branching, it kind of complicates it for a bit. Okay. But this has a lot of the properties that you would expect from this formula. Yeah. All right. Any questions on this?
Those are both rows, right?
Yeah, so both rows. Yeah. Mhm. Okay. All right, and so for the last 10 minutes, I want to talk about the effect of turbulence in your cardiovascular system. All right. So have you guys discussed turbulence in your fluid mechanics classes before, like 333? And so you guys are kind of aware of it, right? So if you didn't, it's okay. It's but so you've been on an airplane. You've been on an airplane with turbulence, right? And so, you know, I think that kind of gives you a good sense of what it is. Okay? And so when we say that a flow is turbulent, we basically say that the flow is really chaotic and difficult to predict. Okay. As a side note, you know, since we're talking about research personalities before, turbulence is also another one of those fields where you have where the heads of the field have very strong personalities and they hate each other. And so if you go into a conference, talk about turbulence, you should be ready for a fight because people have very strong opinions of turbulence and they're very different opinions on turbulence. And so, you know, we haven't advanced much in turbulence either, partially because of that. Okay. And so, you know, if we look at kind of the blood flow in kind of two separate cases, right? If we look at laminar flow, the reason it's called laminar is because the flow looks like nice lamellae sheets. Okay, and so the blood kind of is you know, kind of follows this nice orderly pattern. If we look at turbulent flow, it's really kind of like just a clusterfuck of flow. And so it's chaotic and it's messy, and so, you know, it's really hard to predict. I mean, there's a general mean forward flow, right? And so, you know, in the mean, turbulent flow will generally move forward, but kind of, you know, if you look at kind of the details, the flow is kind of just going in all different directions, and everyone's kind of doing its own thing. Okay. And so, you know, from an analysis point of view, you know, it's a lot easier to predict laminar flow because, you know, you can come up with a formula for that. But for turbulent flow, it's naturally just a lot more difficult. And so, you know, there's still a lot of research being done on what are some good ways to model turbulence. All right, and so the next question is, how do we determine whether a flow is laminar or turbulent? Okay. Yep, I heard it in the audience. And so the main way that you determine this is to compute the Reynolds number. And so the Reynolds number, there's lots of different definitions of Reynolds number, but I'll give you the definition for pipe flow. Okay, so the definition for Reynolds number for pipe flow is rho times U times D, where rho here is the density. Okay. U is velocity. Mu here is viscosity. Okay. Right, and so you can compute the Reynolds number using this formula. Okay, and generally speaking, if you have some internal flow like pipe flow, if your Reynolds number is less than 2300, okay, and so the cutoff for turbulent Reynolds number in pipe flow is 2300. Okay, and so if your Reynolds number is less than this, then your flow is laminar. Okay. Okay. And so, it's a fair question to ask, whether we're going to have turbulent flow inside your cardiovascular system, because, if we have turbulent flow, that kind of changes a lot of the things that we have to do, because the equations that are used to model turbulent flow are quite different than laminar flow. So you have to think about, what kind of turbulent model am I going to use? Am I going to use large eddies? Am I going to use, Reynolds stresses? It becomes a lot more complicated. And so, based on the typical velocities and based on the typical diameters of blood vessels, luckily, most of the time, your flow is going to be laminar. Okay. And so that's a huge break for us. And so, if we can use laminar flow to describe this behavior, that's a huge boon. And the simulations that you're going to run, the CFD that you're going to run for this project, the CFD solver that you're going to use is strictly for laminar flow. And so there's no features in that solver to account for turbulent flow, which is good because blood flow is mostly laminar. It's one of the few, I'd say one of the few really applied subjects in fluid mechanics where you can mostly assume laminar flow, which makes it really unique, but it also makes it really nice. Okay. But there are still some cases where you see turbulent-like flow in the cardiovascular system. Okay. And so one example of this would be like flow past a valve. Okay. Okay. Right. And so if I can draw a vessel like this, right? remember the way that valves work in the cardiovascular system. They're kind of like these leaflets that kind of open up like a flower petal, right? And so if we draw it, right, even the most functional valves, they don't have leaflets that fully get out of the way. And so even when the valve is fully open, you're going to have, a situation that looks like this, where you kind of have almost like a miniature nozzle that occurs in your blood vessel. Okay. And the thing is, because let's say this is the aortic valve, and so on the one side of this valve is the heart, which is pumping blood as fast as it can, right? What can happen is that you can have these like vortexes that kind of shed off these leaflets. Okay? And so you might have situations where you have blood flow like this, and as soon as it gets past the valve, we have kind of like a vacuum that kind of forms in here. Okay. And so you have kind of flow that kind of, does stuff like that. Because this, again, because the blood has to kind of speed up to get through this smaller orifice, right? But then as it speeds up, right after it gets past the valve, it has kind of a dead zone behind it. So that kind of sucks blood back in, okay? And so you kind of have these, what we call kind of recirculation zones. Okay? And typically when you have recirculation, that's kind of a marker of turbulent flow, okay? And so even though the Reynolds number might not climb above 2300, it's still possible to have some structures like this, which kind of mimic turbulent flow, and they kind of share a lot of their properties. But right after this, it kind of dies down to laminar right after that, okay? Okay. And so kind of the upshot for this is that, most of the time blood flow is laminar, but we can have some cases where it looks turbulent, even though it's not actually turbulent. And actually, flow in an aneurysm kind of exhibits a lot of these properties too. And so even though it's technically laminar, because of the unique geometry of an aneurysm, you get some kind of turbulent-like flow that kind of looks similar to this as well. And we'll discuss that when we talk about diseases later on. All right, any final questions before we wrap it up for the week?
The recirculation zone is laminar still?
It's still laminar, and so even though you see some swirling, but it dies down really quickly, and so it's not like real turbulent flow where it persists, and so it'll recirculate, but it'll die down almost. Okay. All right, and so that's all I have planned for today. So thank you guys for coming out. Hope you guys enjoy the weekend. It's a long weekend, and so remember Monday's a holiday. I know we don't meet on Mondays, but I hope you guys enjoy your Monday off. Okay. No, I will. Okay. All right. And so have a great weekend. And I'll see you guys next week.
This is not related to this class, my resume.
Oh, I think probably if you send it to me in an email, then I can be more active. I think that's usually better. Thanks, guys.